So we are studying the interesting topic. Chapter 6 is linear model selection and regularization. So usually when you construct a prediction model, the biggest interest is how to choose the best model. So the chapter 6 is very practical, and we discussed the 3 methods. One is the variable selection. So that we have many candidates of predictors, then we select a few of them. Suppose we have 100 candidates, then we select the best combination. Maybe only 8 or 9 variables are important. Yeah, so yeah, and so that is the one method, the subset selection. And the second method is the regularization method. So regularization method is basically we keep all predictors, but we have smaller questions. Because the larger questions means that the model is less stable, especially if predictors have some measurement error. So suppose that we predict inflation rate by unemployment rate and industrial production. And the industrial production and unemployment rate have some measurement error. So if coefficients are larger, then measurement errors get larger. So that is not good. So if we have too many predictors, we have multi-collinearity. So we restrict we penalize the size of the coefficient. Then the model becomes more stable. So that is the second method. And the third method is to summarize the dimension reduction method. So summarize the predictors into fewer number of predictors. So not choose, but to summarize it. Then we only use the summarized information for prediction. So that is the third method. And we are studying the third method. And the last time we studied the principal component regression. And this time that we use the partial least square regression. So yeah, maybe we go to the partial square. So the method, the difference is the whether or not we use the response variable to make the model. So yeah. So originally we are thinking about the prediction problem, so that we have x1 to xp. But we want to predict y. Right? And the principal component regression, I would say PCR. So that is that we summarize x1 to xp into just the fewer number of predictors. So d is much smaller than p. Then we predict. So this summarize. Then we use the z1 to zd to predict y. Okay. So originally we observed x1 to xp and y, but summarize x1 to xp to z1 to zd. Then we use z1 to zd to predict y. And today we study the p principal, the partial least square. So partial least square, basically we use the information of x1 to xp and also y. Maybe I will say that still we summarize x1 to xp, but we use the information of y. So with considering y. Okay. Then we summarize z1 to zd. So then we explain the z1 to z. We use the z1 to zd to predict y. So in some sense, it's a little ad hoc because to predict y, we before summarizing data, that we use the information of y. So it's a little ad hoc, but still it can be useful for the test error, to minimize the test error. Yeah, so for example, we think about the predicting the inflation rate by several definitions of unemployment rate for each state. So we have maybe 300 series of unemployment rate, and we want to summarize that information to predict inflation rate. Yeah, but maybe that includes the unnecessary information to predict consumer price. For example, if we have the 50 states, the unemployment rate for 50 states, then maybe we can see the difference in unemployment rate by temperature or something. But that isn't probably important for the inflation rate for the macroeconomy of the United States. So we want to use the just useful information in x1 to xp to predict y. So if we consider the what response variable we want to predict, then we can more efficiently summarize x1 to xp. So that is the difference between this PCR, the principal component regression, and the partial least square. Yeah, so summarize. The summary really depends on the objective. Okay? So if the business school students study statistics, they summarized statistical results in a different way. So probably they don't care too much about mathematics. So summary really depends on the objective. So that we use the objective, that is y, to summarize the information. So that is the idea of the partial least square. Okay, so this is the algorithm. So it's a little more complicated than principal component regression. So suppose we have x1 to xp and y. Then to determine the first component z1, still z1 is the linear combination of xj. But at first, we regress y on xj, each xj in simple linear regression. So basically, we evaluate how useful each xj is. So that is represented by this parameter phi. So if xj is closer to y, then phi ji is larger. So remember that here that everything is standardized. So all xj has the variance of 1. So if phi ji is larger, so that means the the more variation of y is explained by xj. So basically, this checks if the xj is highly correlated with y, basically. Then we use this phi sub ji to define the z1. So z1 is summation of the phi sub ji xj. So if xj is highly correlated with y, then we have higher coefficient. So in that way, we can optimize the coefficient, the phi ji, to predict y. Okay, so that is z1. So z1 is maybe not too complicated, and z2 a little more complicated. So now that we regress xj on z1. So okay, so z1 has already been extracted. So we would like to get the second more important information, the second most important information. So we regress xj on z1. So z1 is already taken as the most important information. So how about the second most important information, except for z1? Then we regress xj on z1. Then we think about the residual, the rj. So this residual, so we define this as residual, and we regress y on this residual. So we have already decided to use z1. So the next important information is the basically linear combination of the rj. So you can see that so in this way we can get the second most important information. Okay. And the Z1 is linear combination of xi's. Linear combination of maybe xj's. And that means that Rj is also linear combination of xj's. So that means if we take the linear combination of Rj, so this entire quantity Z2, this is also linear combination of xj. So anyway, we are taking linear combination of xj. So in that sense, it's similar to principal component analysis and principal component regression, but we define these coefficients in a different way.
Sorry, Professor.
Yep.
I didn't understand why Rj is a linear combination of xj's.
Yeah. So at first, the Z1 is linear combination of xj's, right? So then you can see this is linear combination of xj. Z1 is linear combination of xj. So that means the alpha j Z1 is also a linear combination of x1 to xj. Then Rj is xj minus alpha j times Z1, right? So Rj is equal to xj minus alpha j Z1. And the Z1 is linear combination of xj, and xj is just one xj. So Rj is also a linear combination of xj, right? So this is the sum of, phi ji xj. So this is linear combination of xj's. Okay. Then we add just 1 times xj. So xj minus alpha j times linear combination of xj. So this is again linear combination of xj. Did you see?
Yes, thank you, Professor.
Yeah, okay. So that's why the Z2 is again, okay, so Rj is the linear combination of xj. And again, the Z2 is linear combination of Rj. So that means a linear combination of xj's. So everything is the linear combination of xj. So just we have slightly different components. And obviously, this is different from principal component analysis because it depends on y. Z1 and Z2 depends on y. So depend on y. So it's a little different. Yeah, and then we continue. So yeah, so we regress the xj on the Z2, right? So the next that we regress the xj on Z2, then we get the residual again, then we define Z3 and so on. And once you get to Z1 to Zm, then we do the same thing. So we regress y on Z1 to Zm. But you can see that if we compare the partial least square with the principal component regression with the same number of terms, so usually the PLS performs better because Z1 to Zm uses the information of y. So that means it has some advantage to predict y. Z1 to Zm for principal component regression have the good summary of information, but the some information may not be useful to predict y. Yeah, so in this sense, it's a little bit vague what, for example, AIC means. So AIC penalizes the number of parameters, but if we use the information of y to summarize the information of x1 to xp, then of course we can choose smaller m. So and still a good performance. So I'm not exactly sure how to fairly judge the models. PLS, the principal partial least square, is a little ad hoc model because we use information of y to define z1 to zm, then we regress y on z1 to zm. So it's a kind of contradictive. But practically, it works better than principal component regression if dimension is high. So here is the graph for the first component, the z1, and this is okay. So direction of z1. So suppose this vector is ab, then a times the first variable population plus the b times advertisement spending is the z1. Okay, and what's the direction of a? This the direction. So for PCA, that is dotted line. So this is for PCA, and this is for PLS. So slightly different. So dotted line, this minimizes. So this direction is, the maximize the variance of projected the data points. So maybe the center is maybe around here. So if all observations are projected to this line, basically the variance is maximized. So that means the this direction, A times population plus B times advertised spending has the most information out of these two variables. But the PLS, also that we consider how useful the variable is. So basically the PLS, if, so suppose this is the standard vector of standard size, then PLS, probably A is larger and B is smaller. Okay, so that means the population is more useful to predict Y. I'm not sure why is sales or something. So population is more useful predictor than advertisement spending. So that's why the PLS is slightly different from PCA. So generally, these two are not too different because anyway, the objective is to summarize data, but the PLS is more specialized to predict our specific Y. Yeah, so this is a overall explanation of PLS, partial least square. Do you have any questions, comments so far? So both methods use linear combination of original predictors, but the way to summarize the data are a little different. So PCA does not use the information of Y, and PLS uses information of Y. Yeah, so here, so here the section 6.4 explains the characteristics of the methods discussed in section 6.1 to 6.3. So traditionally, we have, so sample size n and the number of predictors p, and the n is much larger than p. So that is traditional statistical theory. So asymptotic theory depends on this. So we have fixed p. For example, we have two predictors. The p is equal to maybe 3, including the intercept, and the sample size gets larger. Then the estimate. So so we regress Y on intercept and the first predictor and the second predictor. And if sample size goes to infinity, then estimate of beta naught converges to beta naught, and the estimate for beta 1 converges to beta 1, beta 2 hat converges to beta 2. So this is the typical classic situation. So P is fixed and the sample size gets larger, then more reliable estimate is obtained. Yeah. And typically, so this algorithm takes the time order of n. Okay, so p is small, so we don't really think about it. Maybe this is time order of n times the p cube or something, but the p is anyway small. So basically, it takes the time order of n. So this is, the computationally the good case. So suppose you have 10 times larger data, just you need 10 times more time to analyze the data. So it's not bad. So if you have 1 million data points, then you took one minute. And if you increase the sample size into 10 million, then just you need 10 minutes, not too complicated. Yeah, but these days we have more data with large p and small n, so more variables. So estimate the blood pressure by the 500,000 DNA mutations with 200 people. So that is typical case. So we have, from each person, we have a large amount of data, but the sample size is very small. P is 500,000, N is 200. And in this case, we cannot estimate parameter, right? So because suppose we think about N is equal to 3, P is equal to 3, then, okay, so Y1 is equal to beta naught plus beta 1 x11 plus beta 2 x12 plus epsilon 1, and Y2 and Y3, if we have 3 observations, yeah, we can just identify the data. But if we have the one more predictors, then we cannot really determine beta to beta naught to beta 2. Okay, so if we have n is equal to p, if n is equal to p, this is just the system of linear equation. Okay, so we can just identify beta naught, beta 1, beta 2. But if we have one more term, and p becomes 4, then we have one more predictor, beta 3 times x13, beta 3 times x23, beta 3 times, sorry, the x31. Oh. Then we cannot really identify it. You can see it. Sorry. 2, 1. Sorry. 1, 1, 2, 1, 3, 1. Okay, x 2, 1, 3, 1, 3, 2, 3, 3. So if we have larger p than n, so p is larger than n, then we cannot identify 4 parameters with 3 equations. So in this case, we have to use the maybe shrinkage method, or we summarize the information beforehand. And typically, it has large amount of calculation. We need the large amount of calculation. And without the good algorithm, this takes the time order of p cube. So that is a problem, because suppose we have n is fixed. So suppose n is 200 and the p is 2000. Okay, so 2000 is problematic maybe. N is the 200 and the p is 30. Okay. And then p becomes 60. Then it becomes 8 times more complicated. If p becomes 90, then compared to 30, that is 27 times more complicated. So P comes from 30 to 90. That is possible. If you just gather 3 times more information, that can happen. But the computation becomes 27 times more complicated. Then you have trouble. So this is really computer intensive. So we have to develop very efficient algorithm to estimate parameters. And that is the rich regression and lasso. I'm not exactly sure about the time order of lasso and the rich regression, but I think that is pretty small. Maybe you can search on the internet, and the computer science students sometimes are good at, have a lot of knowledge about it. I think it's less than p square, like the p log p or p square root of p or something like that. So it's not really large. So it's slightly larger than order of p. P cube is certainly a trouble. Yeah. So large p small n problem are really difficult in terms of identification of parameters, but also the computational cost is problem. Yeah. Oh, this is the graph which explains the same thing as the linear system of linear equation I wrote in the previous page. If 20 observations, then we can determine the line. Okay. Maybe at least 3 or more observations that we can measure. We can estimate the line. At the same time, we can estimate the error size. 2 observations that we can just identify the line. If 1 observation, we cannot. So we have to use the regularization method, the shrinkage method. Yeah, that's it. Yeah, so yeah, but the middle school, when you studied the how to represent the equation of the straight line, you studied this, right? So we need just the 2 points. And more than 2 points, that we cannot find the line which goes through all of those points. But the statistics introduce error. So with error, that we can estimate this straight line. Yeah. Yeah, but the American mathematics textbook is good at the middle school level in the sense that they already included this kind of regression line to motivate students to study the equations for a straight line. So when I studied mathematics, that we haven't studied this kind of concepts in the middle school. So more traditional way to study mathematics. So 2 points determines the line uniquely. Yeah. So that's it. And so this slide compares the several methods to choose the best prediction model. So this is talking about the subset selection. So next few slides discuss the subset selection. So we have P, and the P is the predictor, the candidates, number of candidates. So this is the number of predictors, adapted predictors. Chosen. And this textbook mentioned that the cross-validation is probably the best method to determine the subsets, to determine the best set of predictors. And they mentioned that the AIC, the Marlow's CP, basically these two are similar. And the BIC, it chooses slightly a smaller model. These are unstable due to unreliable estimate of sigma square. So basically, this means that we have to use likelihood function. So that means that we have to specify the model. We have to assume the specific model. But sometimes that model assumption is not entirely correct, or even if it's correct, then it's really hard to estimate it precisely. So that's why they say the AIC, Marlow's CP, and the BIC are unstable compared to CP. And other thing, training error, this always gets smaller for a larger model. So we cannot use this for model selection. adjusted R square. Okay, so it's adjusted version. So yeah, at least it penalizes a large model, but still it does not work well to choose the model. Usually it selects a larger model than the optimal one. So this explains the situation. So the number of variables that we have, n is equal to 20, and we have the 20 predictors. So p is equal to 20, and what is the best d? And this is the number of variables, predictors, so d. And the d is from 0 to 20, okay? Maybe 1 to 20. And if we use training error, always larger model is better. So larger model is better. So it's monotone decreasing function. And if we use R square, always larger d means the larger R square. So maybe this is too trivial. So we should put the adjusted R square. So adjusted R square, I don't know, probably it's slightly better situation. Maybe like this, maybe adjusted R square. But still, it tends to choose a too large model. Maybe in this case, maybe 13 or something, but probably the best one is even smaller, the 5 or 10. Yeah, and but if we use the test MSE, actually just one predictor is sufficient. Yeah, so the training MSE, training MSE and the R square are not good. Not good to select the model. So we have to use the test MSE or the cross-validated MSE. Okay, so next few slides are interesting simulation. So we have the 20 true predictors. So I would say the true D is 20. But we have the 3 cases of simulation. P is 20, P is 50, and P is 2000. So P is 20. That means that all candidates are true predictors, useful predictors. P is equal to 50. We have a kind of the 30 dummy predictors. And the P is equal to 2000. That we have 1980 the dummy predictors. So useless predictors, just noise. And okay, so suppose that we don't know which predictors are true predictors, and we wanna try to identify those 20 true predictors. And we use lasso. So lasso is basically good to choose the efficient model, so we can drop more variables. And the output is here. So we have P is equal to 20, P is equal to 50, P is equal to 2000. So the true number of predictor is 20, 20, 20. So basically, this is a kind of trivial case. And this is somewhat more difficult. And this is much more difficult to identify best 20. So maybe, okay, so we have, say, x1 to x20 are true predictors. And the x21 to x2000 are just noise. But if we have this many variables, maybe just by chance, one variable, maybe x sub 1212. So this really has a high correlation with y, just by chance. Right? So if we have 1980 variables, then just by chance, the sum of them are really useful, especially when n is small. I'm not sure about the n here. Maybe n is 100. Okay, so n is 100 in this simulation. So it's certainly difficult to identify the true predictors, especially if we have 2000 predictors. Maybe some of them are really, highly correlated with y. Okay, and when p is equal to 20, if we use lasso with cross-validated lambda, then they choose basically the 20 predictors. Okay, so in lasso, we determine lambda, then after that, the coefficient. And if we decided coefficient, you can see which the variables have the non-zero coefficient. Non-zero coefficient. So this just reports the number of non-zero coefficient. Okay. And actually, the number of non-zero coefficient. Yeah, this is the number of non-zero coefficient. And the number of non-zero coefficients, that if we have the 21, so that means that we use all predictors plus intercept, then test error is smallest. So this is test error. So basically, we correctly, got the information that all predictors are useful. So how about p is equal to 50? Actually, they choose 28. So here, maybe too small, but the 28. So that means the lasso suggests that we need the 27 predictors, not 20, 27. So that means maybe out of x21 to x50, the 7 of them really have the high correlation with y. So lasso judged that we should include those predictors. And here p is equal to 2000. Actually the 70. D is equal to 70 is the optimal choice by lasso. So that means that we choose 69 variables. So probably we hope that x1 to x20 are chosen, but we picked up the unnecessary variables, maybe the 49 unnecessary variables, maybe x21 to x69. 69. Yes, so these 49 variables are not true variables, but just by chance, similar to y. So lasso included this. So actually, the lasso is not good at, even lasso is not good at identifying true parameters. So if p is large, then the lasso has difficulty to identify which predictors are true predictors. So this will happen even when we use the AIC or cross-validation. So this is called the curse of dimensionality. So if the dimension is large, just p is large, then it's harder to choose the best model. I mean, harder to identify the true model. So it's fine to include this, maybe. These are just noise. Right? So anyway, we include the important information probably. So it may be fine, and it's the best thing we can do for prediction. But to identify true predictors, sometimes the lasso is not good. Yeah, but in reality, we don't know the truth. So sometimes people don't care. Yeah, so for high dimensional data, even with an appropriate variable selection procedure such as CV, the multi-collinearity is severe. That's true. And the selected set of predictors may not be the unique best set. So okay, so besides the curse of dimensionality, that we have some other problems, such as that we have different sets of predictors, totally different sets of predictors that produce the similar results. And that's possible, and that's a problem when we do some procedures. For example, if we do subset selection, stepwise selection, sometimes it's trouble. So maybe stepwise the selection achieve this one. So this model, select this model, but sometimes this second model is slightly better than the first one, but the stepwise procedure cannot reach this model. So that is one possible case. And also, set of predictors, this is generally a problem. So for example, partial least square method, basically we regress the each y on xj. So many methods use this kind of technique. But this only uses the one variable. So maybe x1 is useless variable, and x5 is useless variable, and x10 is useless variable, x13 is useless. But if we combine this, sometimes this is useful, right? Think about the predicting the consumer price. The x1 is the unemployment rate in East Coast. X5 unemployment rate in Midwest. X10 unemployment rate in West, and X13 for South. And all other variables are less relevant variables. But if we only use the Midwest unemployment rate, probably it doesn't have a good power to predict nationwide inflation rate. But if we combine these four variables, sometimes it's very useful. So that's possible. But generally, this is difficult to deal with. So because to simplify the procedure, often we just separate variables. We just check the relationship between y and xj. So sometimes we miss this kind of combinations. Okay, so this is chapter 6. We have studied 3 methods. Subset selection, the regularization method, and the dimension reduction. Do you have any questions? And the 3 methods can be combined. So the subset selection and the Rich or lasso, and the shrinkage method, and the dimension reduction. Very high dimensional data, anyway, we have to do dimension reduction. And suppose we use the PCA, the principal component analysis, then maybe after that we may want to use lasso. Maybe if we use the partial least square, maybe we don't have to do that. But the partial least square is a little ad hoc method. So suppose we decided to use the principal component analysis, then, but still we may want to drop unnecessary information. So in that case, we may use the rich regression or lasso after dimension reduction. Yeah, so often 3, then 2, or 3, then 1. That's possible. After subset selection, rich regression, that is not common. After subset selection, that means that we can deal with that data. So dimension reduction is not necessary. But often we have to combine. We have to do dimension reduction first, then subset selection or rich regression, lasso. That's another way too. Yeah, so this is how to deal with the data. And yeah, sometimes we have to expand the data first. For example, we have x1 and x2, and we need to expand the variable x1, x2, x1 times x2, x1 square, x2 square, maybe x1 cube, square root of x1, and x2 cube, square root of x2, maybe square root of x1, x2, and something. Then we reduce the dimension reduction, maybe z1, z2, z3, or something like that. So that's possible. Yeah, so a linear regression expresses just the linear relationship between y and x. But if you expand more variables using polynomial regression, interaction terms, and so on, then after that dimension reduction, then we can deal with more complicated situation. Still, the final model isn't too difficult.
So like that one midterm question where you had x1, x2, x3, and then all the x1, x2, then you could reduce that to like Z1, Z2, Z3 instead?
Yes, that's true. Yes, and that's often really important. Yes, for example, we can use very advanced methods such as the support vector machine or a deep learning neural network, but often just this kind of simple procedure, expand variables and reduce variables, that performs even better than those complicated models. I mean, the more advanced models. Oh, have you heard the news of the Google trend search? The deep learning is really a hot topic in the past few years, but now the number of Google searches for deep learning is declining. So maybe just because people got used to it, but yeah, maybe it's possibly a new trend that another, the more newer statistical method becomes more popular. So deep learning is really strong method, but probably the most people believe that that isn't really the best method, because obviously it have many problems. The parameters cannot be identified. We cannot interpret the result, and the model isn't really stable. So maybe in the future we can get the more we can get better model. And so the one big advantage of this kind of classic technique to expand the original model, then we reduce the dimension and so on. So these models are generally stable because we are just estimating some linear models and maybe some the lasso or rich regression model. And those models are really good because we have just unique minimizer. So model is stable. So that is a good thing to go. So maybe, yeah, so maybe after maybe this class and maybe one or two more classes, that you want to use more advanced methods. But sometimes the simple model with the classic technique works even better in many cases. Okay, so that is the chapter 6. So today we want to cover some of the code for chapter 6. Chapter 6, I have the 2 files for the lab session. Sorry, I have to go back to the computer screen. And you can see the slide in Canvas I uploaded just before the class. I will share the screen. Okay, and yeah. So in Canvas, you have we have 2 files. The one is the chapter 6 lab session, the section 2, 6.2, and another is 6.3. Maybe I would explain this. Yeah. Okay, so chapter 6.2 is regularization method. So that is the rich regression and lasso. So we do this by using the glmnet function. And we use the hitters data. This is the baseball data. So we use this data in the ISLR, Introduction to Statistical Learning with R package. So yeah, we can see, okay, so after loading these libraries, hitters data is here, and some line have NAs. So often the data set have some NAs, and if some observations have okay, so some variables are missing for some data points, then we cannot use that data points for regression. So if we use na.omit function, then we can remove all lines with one or more NAs. So this is a convenient procedure. If we don't have this, still we can do that with the is.na function, but this is really convenient to remove all NAs. I mean, all lines with at least one NA. Okay, then we do.
Sorry, Professor.
Sure.
It's not better to just remove the cell, not the whole row, because I think maybe there are some good information in the whole row in other column. Just remove the cell that is not assigned, that is NA.
Yeah. So the the command na omit removes all NAs. So okay, so let me see. So for example, okay, so suppose that you can see the data. So suppose that x1 is the maybe the 1, 2, 3, then NA. Okay, and x2 variable is okay. So 10 NA, 30, 40. Okay, then we can define the data frame of x1, x2. Maybe we define this as D. Then, oh, sorry, D. Then D is here. Then NA omit D. So this basically removes all lines with one or more NAs. So only third line and first line and third line remain. Okay. So because, for example, if we want to regress x1 on x2, we cannot use this observation, and we cannot use this observation either. So that we want to omit these lines, then for that purpose, we can use na.omit function. Okay, so yeah, then we define the model matrix. So this is data matrix. So if we express the regression model as the y is equal to x times beta, then this is model matrix is the x part. Then model matrix, the salary, the tilde, dot, the hitter, -1. So yes, so the model matrix, so the salary is the response variable. So this is y. So we use the other variables as x. So that is one thing. But the model matrix is a matrix. So if we have a factor, for example, the league is a factor, so this becomes indicator function for n, and the division indicator function for w. So if we have factor variable, it makes just the matrix. If we have a factor with 3 levels, for example, A, B, C, we have indicator variable for B and indicator variable for C. So it becomes numeric. So in this case, actually, we only have the factor variable up to 2 levels. But anyway, so model matrix becomes the just the numeric matrix, the mathematical matrix. And y is y. And okay, so now that we want to regress y on x and the rich regression, we have the many predictors. The at bat, this is the this is baseball data. So the maybe at bat in the season, number of hits and number of home runs and runs and the RBI. What is RBI? The anyone good at
runs batted in.
Oh, runs batted in. Okay, I see. Runs batted in and the walks and the years is probably okay. So this is the sample unit is a player. So maybe the 14 years in the major league or something. And I don't really know, but the this is maybe you can see the help of the function. But anyway, so the performance, the measures. Then after that, the salary. So we want to predict salary by performance. And we do rich regression. And remember that the rich regression have lambda value, right? So we have to optimize lambda. So we put several values of lambda, and we have no idea what lambda is true. So I use just exponential scale. We start with 0.01 and 0.1 and 1 and 10, 100 up to what? This is the 10 billion. So 10 billion. And usually the lambda is not that sensitive. If lambda is equal to 2000 and 2500, the results are really similar. So usually exponential scale is fine. So we think about the 13 different lambdas, and we want to see how coefficients look like. So we regress salary on, I think the 13 variables or so. I don't know how many variables, 20 variables. So except for salary, that we have 19 variables. So we have 19 variables. So yeah, we estimate 19 plus 1 parameters, and we want to get those parameters for each value of lambda. Okay, so lambda penalize the size. So if large lambda, coefficients get smaller. And this is the graph. Okay, so maybe it's easier when we see the lambda value here, but actually this displays the resulting the sum of coefficients in rich regression. Maybe the sum of squared coefficients in rich regression. L1 norm, GL, sorry, rich regression, alpha is equal to 0 and fits the loss. So if alpha, yes. So actually this should be, maybe this is L1 norm. Probably this is L2 norm, but anyway, so this basically we penalize the summation of the absolute value of beta j square, summation over j, so that we just this graph put the sum of the square of beta j's in the x coordinate. So lambda is larger, we penalize more. So lambda is large, that is the this side, and lambda is small, basically this side. So lambda is getting larger, then coefficient shrinks to 0. And these different graphs have the different coefficients. So green is the coefficient for specific predictor. And this is the result. We have the different lambdas. So first one, the lambda is 1 over 100, right? So 13 variables. So yeah, so the rich regression here. Okay, so so the first one, I think it's in the opposite way. Yeah, I don't know, but the other way around. So the first one, it corresponds to the largest lambda. So lambda is 10 billion. The second one, second column, that corresponds to the coefficient with lambda is equal to 1 billion. Then 100 million, 10 million, and a million, and 100,000, 10,000, and 1,100. And this is 10, 1, and 0.1 and 0.01. So lambda is small. It approaches to the usual linear regression result. So most coefficients are non-zero. Most coefficients are non-zero. As lambda gets larger, all coefficients get 0. Probably this division W, I don't know what that means, but this division W, so this is probably the most significant predictor. Even large lambda, the coefficient is constantly negative. So yeah, more important information. So then this summarizes the result. So probably this green line corresponds to the coefficient of the division W. Division W, I don't know. Some Western League or I don't know. Yeah. And this is the lambda value for rich regression. Yes, so the 7th one. And the coefficient summation, yeah. So we specified lambda from the 0.01 to 10 billion. So the 7th value of lambda is the 10,000. And here the coefficient, and the negative one means that we exclude the first coefficient, because usually we do not penalize the intercept. Okay, so we don't penalize the intercept, so we just exclude this intercept part. Then the other part, basically we have the beta j, so beta j square, the sum of beta j square. So this is the 7th column. So if lambda is 10,000, the sum of the beta j square, beta sub j square is 52.2. Lambda 9th value is 100, and the sum of coefficients, the squared coefficient, is the 13,000. So lambda is smaller, so less penalty on the size of coefficients. So total size of coefficients are larger. Yeah, and that's it. And the yeah. Coefficients, yeah, and this is S is equal to 50. I think that this S is the another name for lambda. S is equal to 50 type coefficients. Yeah, so 0 to 20. Yeah, so we get the coefficients. So once you determine lambda, that we can determine the coefficient. So that is the rich regression. So now that we want to optimize the lambda. So what's the best lambda? And to optimize lambda, we have to do cross-validation. And the cross-validation, but okay, so cross-validation. Yes, so cross-validation. So we use the different lambda, then we evaluate the, so sorry, we use the specific, okay, so we at first divide the data set into training set and a test set, and use specific lambda to train the model with training set. Then we evaluate the test error with test set. And that can be done by this procedure. Yeah, so we can define the training set and the test set, and you can evaluate the variability. That's possible. And yeah, I think that still we didn't really start the cross-valid. We start optimizing lambda. So just if we do validation approach here, that we divide the data set into training and a test, and what happens for the sum of squared errors for test set. And this is just the test set, the response in the test set minus the average of test set. So total variation of the response variable. And if we do rich regression, then, sorry, the total variation is the 224,000. But if we do the rich regression, then the error size, the value of the variance of errors is equal to 142,000. So that means about the 2/3 of the original data. So that means that if we use rich regression with this parameter lambda, then we get 1/3 reduction. So basically, we can explain the 1/3 of variation in Y by this rich regression model. So now we want to optimize lambda. So alpha equal to 0, this just means the rich regression. Alpha is equal to 1 means the lasso. And the cross validation, then we get this. So this is what? This is the log lambda, so the log of lambda value, and this is the mean square error. And the mean square error always gets larger if lambda is large, because we have bias. So lambda is large. We penalize the model. So model becomes simpler, but the training error, so this is training error gets larger. And that's natural. Then plot, yes. Then we use the lambda minimum CB out, so plot yeah, it sounds this is training error, but we wanna minimize the test error by the using this the cb.glmnet function. So if we specify lambda.minimum, basically the R calculates the lambda at which the test error gets smallest with this cross validation. Probably it has the default value of k, so we have probably 10-fold cross validation. You can see the help. So you are doing the 10-fold cross validation here. So the default value is 10. So basically, they did the 10-fold cross validation and optimized lambda, and we can deduct that information from here. So the 25.5. So that is the minimum value. I mean the lambda, the best lambda to minimize the test error. Cross-validated error. Then cross-validated error is the 113,880. So this is the best lambda. Then this is questions. So that we use the best lambda. Lambda is equal to the b dot lambda. So this is 25. So that we optimize the parameters. So these are the best estimated questions. And that's it. Yeah, so rich regression does not make many questions 0. So some questions are small, but still not 0. Okay, so rich regression questions get smaller, but not 0 usually. No questions become 0. And the lasso, so lasso makes more questions 0. And the format is almost similar. So we use the GLMnet and the training, the predictors and the response, and alpha is equal to 1 means lasso. So yeah, so you can see that the lasso is basically we have the absolute value of beta, so that is beta to the first power, and the rich regression is the absolute value of beta to the second power. So the basically 0 corresponds to 2, and this alpha is equal to 1 corresponds to 1. So if alpha is 1.5, then I think that probably the R calculates the R penalized the absolute value of beta to the 1.5th power. And the lambda is equal to grid. Yeah, so last time we defined the lambda values from 0.01 to 10 billion. So then that we get this. So now that this is L1 norm. So that this is the summation of the absolute value of beta j's. So larger lambda corresponds to smaller coefficients. So 0 corresponds to the lambda is equal to infinity. And this is, I think, the right end is the same as linear regression. So lambda is equal to 0. We tried the 0.01, so maybe lambda is equal to 0.01. Here, lambda is equal to 10 billion. And this is the test error. I'm not exactly sure. So last one, the lambda, so this always increases. Yeah. So at least for this figure, so this is the test error. So the test MSE by lambda. So this is the minimized when lambda is equal to 1. Oh, sorry, the last one also it's fine. So okay, so the lambda log 2 for. So sorry. So last one, okay, so this is a little confusing. So this is also the test MSE, and it optimized at this point, maybe 3.5, but actually this is almost the left end, so it looks really hard, but it continues here. So probably it increases around here. And actually the test MSE is minimized at the lambda, log of lambda is equal to 3.5. And the log of lambda is equal to 3.5 corresponds to e to the power 3.5, right? So e to the power 3.5 is the e square is 7.2 or something. So it's 20 something, and that comes here. Okay. So actually this dotted line means the minimum. So minimum. So here, this is the minimum. So here it's easier to see. So this slight increase here and a slight increase here. So this is the minimum. So lambda is equal to probably 0.5 to 1. And actually the log of lambda is 0.5. So that is about 1.8. Lambda is 1.8. And this is the best lambda. Then this is the minimum cross-validated mean error. So this was for rich regression, the 113,880. So almost the same, slightly better. Lasso is slightly better. And here, the many coefficients are 0. So Lasso penalized the coefficients in that way. So if the coefficients are small, that shrinks to 0. So only fewer number of non-zero parameters. Still, maybe except for 4 parameters, it's non-zero. But that is Lasso's estimate. Lasso's estimate looks slightly better than rich regression because this test error is cross-validated error is smaller. Okay, so this is the 6.2. So next time we cover the how to do regression, how to run the principal component regression and the partial least square.